Now I'm going to explain how the correlated detections occupancy model works in a spreadsheet. The spreadsheet's similar in layout to other spreadsheets in the tutorial. We have the parameters in the model in the upper left: size, probability of occupancy, size of probability of local occupancy for the first survey, theta 0, probability of local occupancy in a survey given the previous site was locally unoccupied in the previous survey, theta 1 is probability of local occupancy in a survey given the site was locally occupied in the previous survey, and P1 through P4 are the detection probabilities in each survey. Since we use the parameter probability values in the detection history formulas below, I've named the probability values in column D with the parameter names in order to make the formula below easier to understand. Just click on one of the values and to see the cell name change to the parameter name. So that's psi, there's pi, theta 0, theta 1, and P1 through P4. Compute the log likelihood for a set of data. We'll tell the solver function to use the beta values, column C, for the parameters, which are transformed into probabilities here in column D. For this example, we have 4 surveys, and we'll assume there are spatial replicates like segments of a line transect. With 4 surveys, there are 16 possible histories listed in rows 15 through 30. Here we've listed the frequency or number of sites of each history in the observed data set, the probability of each history given the parameters listed above, the log of the probability, number of sites we'd expect if those parameters were the true values, chi-square value, and the probability and log probability of each history under the saturated model. Under this table, we have a summary showing the total log likelihood, the number of parameters, the AIC value, and some other stats we talked about in the tutorials. The key value here is the total log likelihood value, cell B36. That's the value we need to maximize using solver in order to get the maximum likelihood estimates of the parameters at the top of the spreadsheet. In the tutorial, we computed a couple of history probabilities for this model, and even for the simplest histories, they are fairly complicated. In making a spreadsheet, we've come up with a way to make the detection history probabilities much simpler by only considering part of the history at a time. Looking at the sheet below the likelihood summary, you'll see that we've computed the probabilities of partial detection histories. For example, the first one shows a probability of history which starts out with a detection. The probability for this is fairly simple. If you click on the probability, C41, look at the formula bar, you'll see that it's the probability of occupancy, psi, times the sum of 2 possibilities, pi, probability of the survey before the first survey was locally occupied, times theta 1, probability of local occupancy in survey 1, given the previous survey was locally occupied, times P1, probability of detection in survey 1. The other possibility is that the survey before the first survey was locally unoccupied, probability 1 minus pi, times theta 0, probability of local occupancy in survey 1, given the site was locally unoccupied previously, times probability of detection in survey 1, P1. The probability of the second history listed, it starts with 2 consecutive detections, is now very simple. We simply multiply that history probability by theta 1, since we know it was locally occupied in the previous survey, times the probability of detection in survey 2, P2. The third partial history probability is computed in a similar manner. It's the previous history times theta 1 times P3. We can now compute the full history with 4 ones appearing in the table above, cell D30. If you click on that cell, you'll see that it's computed using the history with 3 ones multiplied by theta 1 times P4. History 1110 can be computed using the partial history with 3 ones as well, but there are 2 possibilities for the 4th survey. It may be locally occupied, given that it was previously locally occupied, probably theta 1. and not detected in survey 4, or it may have just been not locally occupied in survey 4. The partial history probabilities for histories which end in 0 can be computed similarly, except that we have to compute two values for each partial history. One value assumes that the site was locally occupied in the last 0 survey, and one value assumes that the site was locally unoccupied in the last survey. This is so we can use the appropriate theta parameter when building histories based on these histories. For example, a history that starts with just a 0, we compute the probability assuming the site was locally occupied in survey 1. As psi, probability of occupancy, times pi, probability is locally occupied before the first survey, times theta 1, times 1 minus p1, plus 1 minus pi. That's the probability it was locally unoccupied before the first survey, times theta 0 times 1 minus p1. For the probability of this history, assuming it was locally unoccupied, the equation is similar, but we don't need the detection probabilities. So it's psi, probability is occupied, times pi times 1 minus theta 1, plus 1 minus pi times 1 minus theta 0. Other partial histories can be computed by building on the previous partial histories in the same manner. With these detection history probabilities, we can now call the solver function to find the combination of parameter values which maximize the log likelihood value. First, we'll clear out the beta values. Notice that the blank values are interpreted as zeros, which translate into 0.5 for the probabilities. To get to solver, we'll click the data menu, then click solver on the far right. We need to tell solver which cell we'd like to maximize, so we put B36 in the set objective box. Next, we enter the cells that solver can manipulate to find the maximum likelihood line, maximum likelihood value by changing variable cells box. And we put C4 to C11 here. Since all beta parameters are allowed to take any values, we don't need to set any constraints. Finally, we can click solve, and you should see that solver has changed the values, the beta values, and found a log likelihood value. In this case, it says it's found a solution, and the maximum log likelihood value is negative 508.61. So the maximum local likelihood estimates, the parameters are in D4 to D11. This tells us the best estimate for occupancy is around 70 psi equal 0.72%. The pi parameter is not biologically interesting, as it's just a result of where we happen to have started the surveys. The theta 0 parameter is around 28%, and the theta 1 parameter is around 66%, which makes sense, as we probably expect local occupancy to be higher in segments where the previous segment was locally occupied. Detection probabilities indicate this is a very easy to detect species. Now let's look at how to simulate data under the assumptions of this model. On the right, columns R through AC, we have the data simulation section. First, we have our true values of the parameters. Notice that we've named the cells. If you click on one of these cells, you'll notice that we've named the cells with the name of the parameter prefixed by a T for a true value of psi, true value of pi, true value of theta 0, and so on. Next, we specify the number of sites as 250 in cell X6. Below that is a table we use to simulate occupancy, local occupancy, and detections for each site. First, click on cell S9. we see the formula for simulating the occupancy state in site 1 for site 1. Occupancy status is simulated by generating a random number between 0 and 1 and comparing it to the true occupancy parameter psi. If the random number is less than the true psi value, the true is returned in the parentheses and 0 is added. In Excel, true is equal to 1 and false is equal to 0, so the cell will have a 0 if it's unoccupied and 1 if it's occupied. Once we've determined occupancy, we can simulate whether the site was locally occupied in each survey. First, we need to simulate local occupancy before the first survey, so we can use the appropriate theta value in the first survey. We compare a random number with the true pi value. Instead of adding 0, we multiply by the occupancy value we just computed in cell S9. This assures us that the local occupancy will be 0 when site occupancy is 0. Next, we can move on to the first survey. Looking at the formula for this cell in U9, it's a little more complicated, but it follows the logic of the history probabilities. We start with S9, which is 1 if the site is occupied, 0 if not, then multiply it by the sum of two possibilities. First, the site is locally occupied before the first survey, T9 equal 1, and the second possibility is the site is locally unoccupied before the first survey, T9 equals 0, 1 minus T9 would be equal 1. Then we compare a random number with the appropriate theta value and multiply it. For surveys 2 to 4, the formulas are exactly the same as the first survey. Once we've simulated local occupancy for each survey, we can simulate detection in each survey. This is done by multiplying the local occupancy state in each survey by comparing the comparison of the random number with the detection probabilities. So U9 is the local occupancy state in survey 1 times, here's where we compare the random number with the detection probability in survey 1. In the last column, we've just pasted together the 4 occupancy states across into a string. These have been summarized in the middle cells N25 to O40. If we want to get the maximum likelihood estimates of parameters for the simulated data, we need to copy the summarized frequency up to the presence input table above. Copy the frequencies with Control-C, and we paste them into the presence input table here. And I'm not going to use Control-V. I'm going to right-click and select Paste Values. That will paste just the numbers in the formula. Once you've pasted the values, the table on the left will update with those frequencies. We can use Solver to find the MLEs for the newly simulated data. Okay, I take that back. We need to also paste these frequencies into the table on the left here as well. So I'll right-click. Need to copy first. Control-C and then paste over here. Paste the values. Now we can use Solver to find the maximum likelihood estimates for the newly simulated data. And this procedure for that is the same as we just did at the beginning. One last thing, I've included instructions on how to analyze the simulated data using our presence. The code here reads the input from the clipboard, so we need to copy cells L4 to P19 to the clipboard. That's the area in gray here. Copy that to the clipboard, then run the code below in R. Run this code in R. Before we do that, we need to copy the code to RStudio, then come back to Excel and copy the data to the clipboard, and then go back to RStudio and run the code. I hope this helps in understanding how the correlated detection model works. Thanks for watching the video.